In this video, we're going to be looking at topic 2D, the reactivity series, and this is part of the IGCSE chemistry course for Edexcel, and we're going to be focusing on the double science content. So for double science, you need to be able to arrange the metals in a reactivity series for the specific metals in the third learning point there, and you should be able to do this by looking at their reactions with water, dilute hydrochloric or sulfuric acid, as well as their displacement reactions. We should also know the conditions under which iron rusts and how we can prevent the rusting of iron using various methods, as well as understanding the key terms of this topic, such as oxidation, reduction, redox, oxidizing agent, and reducing agent. So let's start off by looking at what the reactivity series is. Well, the reactivity series is a series of metals in order of reactivity from the highest to the lowest. So at the top of the reactivity series, we have metals such as potassium, sodium, and lithium, and these are the most reactive. And they go down through calcium, magnesium, aluminium, zinc, iron, copper, silver, and gold, which is down to the least reactive. Now, there are a few other metals that can be in the reactivity series, but you're not expected to memorise them. However, you may find it useful to expand where some of these are going to be so that it helps you with your predictions should you do it. Now, you can see that we also have carbon and hydrogen in the reactivity series, and we use these as a sort of benchmark. The carbon is used more for triple content when we're talking about extraction, and the hydrogen is used as a way to figure out when something is going to react with an acid or not. So the metals at the top of the series, as we said, are the most reactive, and the metals at the bottom are the least reactive. Now, we can take what we've seen with displacement reactions previously in the Group 7 topic and apply it to metals. So previously we said that a displacement reaction is when a more reactive halogen took the place of a less reactive halogen in Group 7. Now, here the process is the same, but we simply have swapped out the word halogen for metal. So a displacement reaction occurs when a more reactive metal takes the place of a less reactive metal in a compound. So the metals that are higher on the reactivity series can replace a metal that is lower from its metal oxide. And these are sometimes known as competition reactions because basically what's happening is these two metals are competing or fighting to bond to the oxygen. So let's look at an example. If we take magnesium, which you can see is here on the reactivity series, and we react it with copper, which is much lower on the reactivity series, and react it with our oxide of copper, we are going to get a displacement reaction happening. And what happens is the magnesium takes the place of the copper, and these two things swap out. So we go from magnesium and copper to oxide to magnesium oxide and copper. Now, this reaction is very explosive, and at the end there are traces of white magnesium oxide left because the copper has been displaced by the magnesium, because the magnesium is the more reactive. Now, some key terms that we have to know when we're talking about these sorts of reactions. We call these reactions redox reactions, and it is because we're getting two separate chemical reactions happening. We're getting something called oxidation and something called reduction, and these two things always happen hand in hand. There is no way for oxidation to happen without reduction, and we shorten these to redox. And we can explain this in two ways. We can either look at it as the transfer of oxygen, or it can be the transfer of electrons. So let's have a look to see what that actually means. Well, if we have a reaction where something is gaining oxygen, then we call this oxidation. So a metal that can gain oxygen, so for example, magnesium becoming magnesium oxide, we say that this has been oxidized, and because it is gaining oxygen. If we have a loss of oxygen, then we say that the substance has been reduced or has undergone a reduction reaction. So in the case that we just looked at, the magnesium gains the oxygen, so it is oxidation, whereas the copper oxide is losing that oxygen, so it is reduction. You can see that these two things have to go hand in hand. Now, the most common way that we will explain oxidation and reduction isn't actually through the gain or loss of oxygen, it is about electron transfer. And oxidation is the loss of electrons for a substance, and a reduction reaction is the gain of electrons. So what this means is that one species in a reaction is going to lose electrons, and those electrons that are lost are going to be gained by something else in the reaction. And because these two things happen together, we call these redox reactions. And you can help to remember this by using the mnemonic oil rig. So oil rig stands for oxidation is loss of electrons, reduction is gain of electrons. I would strongly recommend that you memorize this mnemonic. It can be very, very useful. So let's look at our same example of magnesium and copper in terms of the atoms and ions to show the electron transfers. So here we start off with magnesium being an atom, and when it goes to form the magnesium oxide, I can write the ionic formulas, and we can see that the magnesium becomes a magnesium 2+ ion. So the magnesium, this here, has lost electrons. So because it has lost electrons, remember oil rig, that tells us that the magnesium is oxidized. The copper has went from copper 2 to copper metal. So here, this copper is gaining electrons. And when it gains electrons, that means that the copper is reduced. Now, what we can actually say is happening here is the magnesium is losing 2 electrons, and it is giving those 2 electrons to the copper ion. So the electrons are not shown in the equation because all they are doing is being transferred from one species to another. Now, we can also get displacement reactions with metals and aqueous salts, and this works in very much the same way. So if we take zinc, for example, and this time instead of copper oxide, we're looking at copper sulfate. So we're looking at the salt. But we get the same thing. Zinc is more reactive than copper because it is higher on the reactivity series. So it is going to take the place of the copper, and we are going to form zinc sulfate and copper metal. Now we can write this out in various different ways. We can write it as a word equation. We can write it as a chemical equation. And then we can take that chemical equation and convert it into an ionic equation. And that shows the different ions that are present. And this way it allows us to see what is being oxidized and what is being reduced. So we've got zinc metal becoming zinc ions. And we have got copper ions becoming copper atoms. Now what you can see is that the sulfate here is exactly the same on both sides, and we call this a spectator ion. So this just means that it is unchanged in the reaction. And what we do is we remove these from the equation. If it doesn't change, it's not important to us. So rather than cluttering our equation with extra terms that aren't actually taking part in the reaction, we call them spectator ions and we simply remove them. So if we've taken those spectator ions out, it leaves us with this equation here. And what we can see is that the zinc is losing electrons, whilst the copper is gaining electrons. So the zinc is being oxidized and the copper is being reduced, because the zinc is losing its 2 electrons and it is giving it to the copper in order for them to gain to become an atom. Now we can even take this one step further and we can split this reaction to show the movement of electron between the two different species. So we can show that when an oxidation reaction happens, we start with a zinc atom and then we go to a zinc ion, and because it has lost 2 electrons, I have to write how many electrons have been lost. So I get an equation that looks like this, where I've got the zinc metal giving you zinc ions plus 2 electrons. For a reduction reaction, we start with the ion. We then have to show the gained electrons, and then we form our atom. So notice that for an oxidation, the electrons are on the right hand side of the arrow. And for a reduction, the electrons are on the left. So they are on the right for an oxidation because they are being lost, but they are on the right because they are being gained. And we call these ionic half equations. And we call them a half equation because they only show half of the redox reaction. So they're either going to show an oxidation or they're going to show a reduction. And sometimes you can see them being called ion-electron half equations. And that is simply because they contain ions and electrons, and they are showing half of the redox reaction. Another key term that we have to know linked into this topic is oxidizing agents. Now this can be quite tricky, so make sure to pay attention closely. Oxidizing agents are substances that will oxidize something else. This means they either give away oxygen or they gain electrons. Okay? And by gaining electrons, that means that they themselves are reduced. So let's have a look at that in a bit more detail. If we take our zinc and our copper, in this case, the copper ion is going to gain electrons to become a copper atom. Okay, so it's going to gain electrons, and that means that it is being reduced. But in order for the copper to be reduced, it has to take those electrons from somewhere else. And it takes electrons from the zinc. So the copper causes the zinc to lose electrons so that the copper can take them to become the atom. So by causing the zinc to lose electrons, the copper is causing the zinc to be oxidized. So we call it an oxidizing agent. It's very important that we understand that oxidizing agents cause something else to be oxidized, and by doing that, they are reduced. So in this case, the copper acts as the oxidizing agent. Now we can also look at this from the other perspective, and we can look at a reducing agent. A reducing agent is a substance that reduces something else. Okay, and it does this either by gaining oxygen or giving away electrons. So reducing agents themselves are oxidized. So in this case, our zinc is acting as a reducing agent because our zinc is going to gain electrons. It's going to lose electrons. Okay, when it becomes a zinc ion. And in order for it to, when it loses its electrons, those electrons have to go somewhere, and it gives the electrons to the copper, causing the copper to become reduced. So the zinc acts as a reducing agent because it causes the copper to be reduced, but the zinc itself is oxidized. hopefully that makes sense, and we'll be able to see this a bit more in practice. So let's have a look at reaction. So we've got reaction between copper and silver nitrate, and we want to write this out in various different ways. So let's start off with the word equation. We're going to have copper plus silver nitrate, and this is a displacement reaction. So the copper is going to take the place of the silver. So we're going to make copper nitrate plus silver metal. Now we want to write out the chemical equation for this, and we want to include state symbols where possible as well. So we have copper metal reacting with silver nitrate, which is aqueous, to give us copper nitrate, which is aqueous, plus silver metal. And of course, we have to make sure that this is balanced. So we have 2 silver nitrates and 2 silvers. So now we want to write out the ionic equation for this. So what you would do is write out each thing individually into its different ions. And what we would see is that our nitrate, which is NO3, is a spectator ion. So we would remove that. So let's rewrite this as ions, but without the nitrate. So we're going to have copper metal reacting with 2 silver ions, giving us copper 2 plus ions and 2 silver atoms. That is our overall ionic equation for this reaction. Now we can even take it a step further and we can write out the half equations. So if we start with the copper, we're going to have copper metal forming copper ions. Now here we are losing the copper ions, so the electrons from the copper, so that goes on the right hand side. Then we have silver, so we have 2 silver ions forming 2 silver atoms, and that means that each of them have to gain 1 electron. But because we have 2, we are gaining 2 electrons here. So the copper is losing 2 electrons, and those 2 electrons are being collected by the silver to form silver atoms. So when we want to look at what one is the oxidizing agent and what one is the reducing agent, well, the oxidizing agent is the one that is going to be causing something else to be oxidized. And remember, we have oil, rig. So the oxidizing agent is causing something to lose electrons. So in this case, the silver is causing the copper to lose electrons. So our oxidizing agent is the silver. And our reducing agent, and so it would be the silver nitrate. And the reducing agent is going to be our copper metal, because the copper is causing the silver ions to be reduced. And you can see that we have those answers there. So now let's look at the reactions of the different metals in the reactivity series with water. Any metal above hydrogen on the reactivity series is going to be able to react with water or steam, and they're going to produce hydrogen. So if we have metal and cold water, we're going to form a metal hydroxide. And if we have a metal and steam, we're going to form a metal oxide. As you go down the group, the reactions become less vigorous to the point where they will not happen anymore, and metals below hydrogen do not react with water. We can also react these metals with acids, and these will react to form a salt and hydrogen. And again, this is metals above hydrogen are going to react with acids to form our salt and hydrogen. So we can have, for example, a metal plus hydrochloric acid giving us a metal chloride, or a metal plus sulfuric acid giving us a metal sulfate, both times making hydrogen gas. Again, as you go down the group, the reactions become less vigorous, and the metals like zinc and iron actually need heat in order to rapidly react with acid. So what you'll find is that they may still react, but just very slowly, and if we want it to get to be a fast reaction, then we need to heat it. And any metal below hydrogen do not react with acid. So we can make predictions for metals that are unfamiliar to us in terms of the reactivity series. And we can predict where it's going to be or how it's going to react. And we can do this using 3 steps. So the first thing we would do is we would add a small piece of the metal to cold water. If it's going to react fast, that means it is a very reactive metal. So it's going to be above magnesium on the reactivity series, because those are where your very fast reacting metals with cold water reside. If there is no reaction, then what you would do is move on to testing it with acid. And if there is a reaction, it is with acid, it's going to sit somewhere between magnesium and hydrogen. If there is no reaction with either with acid or with water, then the metal is going to be below hydrogen. Now, you may not be able to specify exactly where on the reactivity series, but you can make an educated guess between the top, the middle, or the bottom. Now let's move on to the last part, which is rusting of iron. So iron is going to rust in the presence of oxygen and water. And rusting happens when iron and steel form iron 3 ions, and we get this oxidation reaction happening. And what happens is the iron is going to form a substance called iron 3 oxide, which is also known as rust. So rust, the proper chemical name, is iron 3 oxide. Now, because rust has a specific chemical name incorporating iron, when we're talking about the reaction of a metal with water or with oxygen to form this sort of damage, we can only use the word rusting for iron. Every other metal, we should be using the word corrosion. So rusting is a form of corrosion, but not all corrosion is rusting, because rusting only applies to iron. So please make sure that you don't use those words interchangeably. Now, it's very important for us to prevent the rusting of iron, because the formation of rust can damage a structure of an object, or it can even break them, and that can cause us a lot of problems if it was something like a bridge or a building or even a car. So there are 3 possible ways to protect iron from rusting. There is the barrier method, there is galvanizing, and there is sacrificial protection. And you need to be able to explain briefly what each of them are. So the barrier method involves putting a barrier between the iron and the water and oxygen. And it basically means that we coat the iron with something, and then it stops the water or oxygen from reaching it. And the most common ways to do this are to paint the iron, to coat it with an oil or grease, to put a plastic over it, or to coat it with a metal lower on the reactivity series. Okay, and that is going to then stop any oxygen or water getting into the iron. If it's something that's lower on the reactivity series, then it means it's not going to react. So you're causing the iron to not be reacting with the water or oxygen, because it simply cannot get to it. Another method is known as galvanizing, and this involves coating the iron with a layer of zinc. And galvanizing is specific that it has to be zinc. And zinc acts as a barrier to the oxygen and to the water. And what it does is it protects the iron from rusting. So the zinc acts as a barrier, but even if there is some scratching and it exposes the iron still doesn't rust. And the reason for this is that zinc is more reactive. it is higher on the reactivity series. And what that means is the zinc is more likely to react with the oxygen or with the water. So the oxygen or water would rather react with the zinc on the surface as opposed to the exposed iron. So the zinc sacrifices itself to protect the iron. So galvanizing is a form of sacrificial protection, which is the last method that we can use. Now, we don't always use zinc. We can use other metals for this, such as aluminium or magnesium, but if we do use zinc, then we call it galvanizing. So sacrificial protection involves attaching the iron to a block of metal that is higher on the reactivity series. And we would use either aluminium, zinc, or magnesium. And what this means is that the more reactive metal is going to corrode before the iron does. So the more reactive metal would rather react with the water or the oxygen as opposed to the iron, and this stops the iron from rusting. So the metal that is higher is sacrificing itself to allow the iron to not corrode. These blocks are known as sacrificial anodes, and they're typically used on very large structures where other protection methods would be quite difficult to use effectively. So if you have a large building or a bridge, you may find that barrier methods such as coating it with oil or grease or paint are too time-consuming or expensive. So what sometimes they may do is have these sacrificial anodes that help protect the iron from corroding, because of course if we get any sort of rust building up, it can cause damage, which could then affect the integrity of the structure and potentially even cause it to collapse. So let's finish off by looking at some past paper questions. So this is from the June 2015 paper. A student carries out an investigation to compare the reactivities of 4 metals, so aluminium, copper, zinc and metal M. He adds strips of the zinc, 2 aqueous solutions of the nitrates of each metal, and then after a few minutes he removes the strips of zinc and examines them. And we can see that we get a table of results here. So for aluminium nitrate, he's seen no change. For copper, there was a brown coating on the zinc. For zinc nitrate, no change. And for the nitrate of metal M, there was a grey coating. So for part A, we want to say name the substance that causes the brown coating on zinc. So that is this reaction here. Well, the zinc is higher on the reactivity series, so that wants to take the place of the copper, and we are going to be forming copper metal, and that is our brown solid. Part B, state why there is no change in the experiment with the zinc nitrate solution. Well, we're taking zinc and adding it to zinc nitrate, and it cannot have any reaction because zinc cannot displace itself. You would only get a displacement reaction with something that is higher on the reactivity series. Or you could even say that the 2 metals that are involved, the zinc and the zinc nitrate, have the same reactivity. Now the student repeats the experiment with strips of metal M instead of strips of zinc, and the table shows the result. So we can see for aluminium, we're getting no change. Copper, we're still getting that brown coating. Zinc, no change. And the nitrate, no change. The nitrate of metal M, no change. So using the information from both tables, place aluminium, copper, zinc and M in order of decreasing reactivity. So the one that is going to be the most reactive is the one that is not going to be displaced by either. So we can see that aluminium has no change in table 2. So this one being table 2. And if we go back to table 1, we can see aluminium also has no change here. So our most reactive metal in this case is going to be the aluminium. For the least reactive, it's going to be the one that is going to be displaced in both. So we can see that copper is displaced in table 2 and copper is also displaced in table 1. So that means our least reactive is going to be copper. Now we just have to figure out which one is going to be most reactive, zinc or the nitrate of metal M. So we can see that when we have the M put into zinc nitrate, we don't get a reaction happening. But when we put the zinc into the nitrate of metal M, we do see a displacement reaction. So that means that zinc must be more reactive than metal M. So our second most reactive is zinc, followed by metal M. So this is using a compare and contrast method of the two tables. So we're having to use all of the information that we are given in order to figure this out. Part D, the magnesium reacts with an aqueous solution of silver nitrate, and the reaction can be represented by this ionic equation. Explain why this can be described as a redox reaction, where you can see that the magnesium is going to be losing electrons and the silver is going to be gaining electrons. So we are getting electron loss and electron gain happening. So then we must have a redox. So we can say that we are getting oxidation or electron loss and reduction or electron gain are both happening. And explain in terms of electron which species is acting as the oxidizing agent. So remember, an oxidizing agent is going to cause oxidation and itself will be reduced. So if we figure out what is being reduced, then we know that that's going to be the one that is the oxidizing agent. So remember, our mnemonic is oil rig. So the one that is being reduced is going to be the one that is gaining electrons. So that is going to be our silver ion. So our Ag plus, or our silver ion, is the oxidizing agent. And the reasons why is because it gains electrons. So remember, we have to say in terms of electrons. So it gains electrons, or it takes electrons from the magnesium, so causing the magnesium to be losing electrons. And that's for 2 marks. You get 1 mark for identifying the oxidizing agent and 1 mark for explaining why. And there's the mark scheme if you want to have a look at it. And let's finish off with the January 2012 paper, which is a question about rusting. So iron is a useful metal, but one problem with iron is that it can rust. Name the compound that is present in rust. Well, that's going to be iron 3 oxide, or Fe2O3. You can write the formula or the name, that's acceptable. 2 substances that are required for iron to rust, well, that is going to be water and oxygen. Or you could write again the formulas H2O and O2. 1 mark for each of them. What type of reaction occurs during the rusting of iron? Well, the rusting of iron is a gain of oxygen, or going from iron metals to iron 3 plus. So a loss of electrons. So that means that if we are losing electrons or gaining oxygen, it must be an oxidation reaction. And galvanizing can prevent iron from rusting, and in this process the iron is coated with another metal. Identify the other metal. Well, for galvanizing it has to be zinc. And identify a suitable object for galvanizing. We want it to be something that's going to come into contact with oxygen and water quite regularly, and it shouldn't be anything that is too large as well. So the best answer here is going to be a bucket. And lastly, 2 other methods that can be used to prevent iron from rusting. There are various different answers here. You could say using oil, using grease, using paint, or even coat with a less reactive metal. Any of those for 2 marks. And there you can see that we have the mark scheme. Now that's everything for topic 2D, the reactivity series for double chemistry. If there's anything you're not sure of, please feel free to leave a comment below, and we hope to see you back on the channel soon.